DNP3 Basics, Lesson 4, Data Link Layer. We will now go over some details of each layer in a DNP3 message. The first is the data link layer. The data link layer is 8 octets in length and looks like this. Remember, in talking about message lengths, that we ignore the CRC octets. The first two octets are always hexadecimal 5 and 64. The third octet, the length, defines the number of user octets in the entire frame. The minimum value of the length octet used for messages that do not contain any application data is 5. This includes the control octet, the 2 octet destination value, and the 2 octet source value. The 564 length and CRC are not considered user octets. The minimum value of the length octet for messages that contain some application data, that is, more than only the data link layer, is 8. This includes a minimum of 3 additional user octets: the transport layer, 1 octet, and at least 2 application layer octets. The maximum value for the length octet is 255. The total number of octets transmitted include the header octets and all CRC octets. Each device in a DNP3 network, both a master and each outstation, is assigned a 16-bit DNP3 address. Each DNP3 message contains 2 addresses, one for the device originating the message, called the source address, and one for the device where the message is destined, called the destination address. Addresses for outstations need to be unique for outstations on the same serial communication line. Messages sent by a master on a serial line are detected by all outstations on that line. The DNP3 address provides a method for each outstation to identify a message as belonging to them. It does not matter what the address is, as long as no 2 devices have the same address. Addresses for devices on different serial lines or devices operating with network connections need not be unique, since a message sent to one outstation cannot accidentally be detected by another. Likewise, a master address, except on a serial line with 2 masters, if such a topology even exists, is not really important. So, in DNP3 messages sent from a master, the destination address is the address of the target outstation, and the source address is the address of the master. Messages sent from an outstation, the source address is the outstation address, and the destination address is the master address. All systems use outstation addresses. Many systems do not require a master address. For these, outstations either do not validate the master address field or commonly assume it to be 0. Some systems do require a master address. If basic communication is failing, then master address setting is a good place to look for a configuration issue. DNP3 reserves addresses 65520 to 65535. That's hex FFF0 to FFFF. Outstations and masters should not use these addresses as device addresses. Within this range, the upper three addresses, 65.533 to 65.535, are reserved for broadcast functions. A message sent to any of these addresses should be processed by all outstations that receive the message. A response is never sent to a message received using a broadcast address. Address 65.532 hex FFFC is called self-address. It is like a broadcast address, except that a response is sent. The source address in the response is the outstation's real address. It is a way for a master to find the real address of an outstation. DNP3 devices may, but are not required to, respond to messages sent to FFFC. The other addresses in the reserved range are not given any defined use within DNP3, but they should not be used as real device addresses. The fourth octet in the data link layer is the control octet. It identifies the type of data link message being sent and is structured as shown. The most significant bit in this octet, dir, is the message direction bit. It is 1 in messages from the master and 0 in messages from the outstation. PRM is a data link primary bit and is 1 in almost all messages. It is 0 only for data link layer only response messages. More on this later. FCB is the frame control bit, which is toggled in each message sent from the device, but only for those messages with the FCV bit set. FCV indicates that the FCB bit is meaningful and should be examined. Function code is, as you may have guessed, the data link function code. There is a different meaning to the function code field depending on whether the primary PRM bit is set or not. Do not confuse PRM or primary with DIR or direction. Both the master and outstation can send primary messages. In fact, almost all messages sent are primary. This table shows a list of data link function codes that we will be talking about in the rest of this lesson. Note that most of the values are not used. Also note that when the PRM bit is set, the primary bit, that only 2 of the function codes use the FCV bit, which is frame control valid. That's values 2 and 3, which is test link states and confirmed user data. Also note that when the primary bit is 0, the function code value could be the same as when the primary bit is 1, but it is a completely different function. So for now, just note these functions and we will talk about them soon. Most messages sent in either direction include application data. Those messages use primary function codes 3 or 4, and almost always 4, which is unconfirmed user data. You may never see a message with any other code. That is, in the normal data exchange between a master and outstation, the master sends an application message to read some data. The outstation responds with the requested data. Both use a data link user data function, almost always unconfirmed user data. Unconfirmed user data does not use the FCV or FCB bits. So the data link control octet in almost all messages from the master is a hex C4, which is function code 4 with the direction and primary bits set. The data link control octet in almost all messages from the outstation is a hex 44, which is function code 4 with the primary bit set. Since the message is from the outstation, the direction bit is 0. The following screen capture shows a read and a response using these two function codes. The other way to send user data is with function code 3, confirmed user data. The same application data can be sent using confirmed user data as with unconfirmed user data. The big difference comes into play when sending multi-frame messages. With unconfirmed user data, the multiple frames are sent in sequence without further input from the receiving station. With confirmed user data, the same frames are sent, but the receiving station has to respond, acknowledging that the frame was received okay, before the transmitting station can send the next frame. Clearly, it will take longer to send a message requiring confirmation than without. Confirmed user data was included for use on noisy communication lines, where it is possible a message would not arrive as sent. If the line is very noisy, then confirmed user data provides a means to identify errors and recover. There are other ways to detect errors and recover, but those are in the application layer and do not come into play until all frames are sent. There is no way to accurately determine if confirmed user data is worth the overhead and delay, since the same overhead occurs when there are no errors. The trade-off against this extra overhead is faster recovery when there are errors. One rule of thumb is that if the line is so noisy that 1 out of 25 messages sent would arrive in error, then it might be worthwhile considering confirmed user data. But that rule of thumb is my thumb. You will not find it justified anywhere. So, confirmed user data messages are allowed, but rarely used. They are required to be supported by a receiving station and somewhat complicated to learn. Listen to this lesson, but the real important thing to remember is where your notes are, so you can refer to them if needed, which may be never. It is kind of like high school algebra. Confirmed user data always uses the FCV and FCB bits. The FCV bit means that the FCB bit is valid. The state of the FCB bit is expected to toggle in each message. The basic logic used to transmit a multi-frame message is: the outstation sends the first message to the master using confirmed user data and setting the FCB bit to what it thinks the master is expecting. The master receives the message and responds with a data link ACK. This is data link function code 0 and primary bit 0. The master expects the FCB bit state in the next message to toggle from the state it had in the current message. the outstation gets the ACK and sends the next frame with the FCB bit toggled. The process continues until the entire application message is sent. If anything goes wrong in this exchange, such as a message received with a bad CRC, any of various recovery schemes may be invoked depending on outstation configuration options such as data link retries. For this class, it is only important to note that confirmed user data can be used as a way to improve communication in noisy line environments. Use in any other environment is a waste of bandwidth. There is one more point worth discussing for confirmed user data, and that point refers to a statement in the prior page that said, the outstation sends the first message to the master, setting the FCB bit to what it thinks the master is expecting. How does it know what the master is expecting? Let's assume the master has started and not yet received a message from the outstation using confirmed user data. So the outstation sends the master a message using confirmed user data. The master does not know what FCB bit to expect, so it sends a NAC to the outstation instead of an ACK. The NAC means the master has no idea what FCB bit to expect. The outstation replies to the NAC message with a reset link. The reset link tells the master to expect an FCB state of 1 in the next message. The master, being happy with this, sends an ACK. The outstation now resends the message it originally tried to send with an FCB state of 1. The master is happy and replies with an ACK. Everything goes merrily on its way. So we just spent 3 frames of the lesson explaining something that you may never see. We could have spent 6, but it is a basic part of DNP3, required to be supported at all subset levels, so we needed to get this out of the way. But before we leave the area of confirmed user data, I have a few final comments to make. First, confirmed user data messages are not allowed on a network. This means they are almost never transmitted. However, there are communication topologies that carry a single message, switching between network and serial equipment. Therefore, network devices that receive confirmed user data messages must support them and respond appropriately. Confirmed user data is useful for serial applications only with noisy communication lines. Otherwise, they just add unwarranted overhead. And they are best suited for messages with more application data than can fit in a single data link frame. Since this is never the case for messages sent from the master, their best valid use case is in outstation responses. So let's review the data link function code table shown below. We've already talked about the functions highlighted in the kind of orange color, and we will now talk about the 4 that remain, which is test link states, request link status, the link status response, and a not supported response. The most common other data link only exchange shown here is to send a link status request and get a link status response. This exchange is commonly called keep alive. used to make sure each side is still alive without interrupting normal communication. In the example, we see the master issuing a request with control octet hex C9, function code 9 with the primary bit set, and the response is function code 11 with the primary bit cleared. Other data link messages and information is used less often. It includes test link states, a message you may never see. It verifies that FCB bits are in sync for confirmed user data purposes. The response, if everything is okay, is an ACK. Do not worry about this in a basic DNP3 class. The not supported function is used as a response for any request with an undefined data link function code, or when a defined function code is not supported. And there is a DFC bit in the data link control octet set in outstation responses when the outstation is too busy or having problems. I have never seen this used. Don't worry about it either. Okay, so finally we are at the end of lesson 4. What have we learned about the data link layer? 1. The 8-octet data link layer is at the start of all DNP3 messages. 2. It defines where the message is going, destination address, and where it came from, source address. It specifies the length, number of octets in the frame. There are several data link function codes, but the one used almost all the time is unconfirmed user data. For systems that use confirmed user data, we learned how to coordinate and use FCB bits, and request link status and the link status response may be used as keep alive messages. This is the final lesson available on YouTube. Lessons 5 to 12 and the summary can be found at www.cdonecal.com.